Hi all, I wanted to sneak one last example in this section that's not a position velocity problem. So nothing too crazy here. I just have a table of data where T is the time measured in minutes and F is the temperature in degrees Fahrenheit, and we're looking at a potato placed in an oven and the temperature is increasing over time. So we are supposed to find an average rate of change from t equals 15 to t equals 45. So again, this is totally a relevant question for the previous section as well, but just to kind of tie back to something that's not position and velocity. So t equals 15 to t equals 45 would be these 2 points right here. So we could take the 296 minus 180.5 and divide that by the 45 minus 15. And I get 115.5 over 40. And if I do that calculation, I get about 3.85. So an average rate of change calculation as usual. And we'd like to track down some units for this. So if we look back at what we did, we took the 296 and the 180.5 from the first column, which means that's a change in temperature or change in degrees Fahrenheit. And the 45 and the 5 were from the minutes column, so that's a change in time, which was in minutes. So our final answer is degrees Fahrenheit per minute. Okay, so there's a couple of things that I want to point out here. If all you're given is a table and you're asked to estimate an instantaneous rate of change, you'll just do the best average rate of change you possibly can. So for example, if I was asked to find the instantaneous, to estimate the instantaneous rate of change at t equals 30, I think this would not be a bad way to do it. So one way you could do it is go from 15 to 30 and then from 30 to 45 and calculate average rates of change and then average them. You can also do what's called, it's like a central limit, central something, where you take the point before and the point after the number that you're actually interested. So 15 was the one before 30 and 45 was the one after 30, and you use those for your average rate of change. In this case, since our times are equally spaced, we go 0, 15, 30, 45, 60, those two ways to estimate the instantaneous rate of change will actually give you the exact same thing. But if your time intervals aren't perfectly spaced the way these are, they will give you a little bit different number, and I think both are great. So there are some questions where you all might get slightly different answers, and that's completely okay. We're just estimating. So yes, this asks for an average rate of change, but that average rate of change is about as good as we can do to estimate the instantaneous rate of change when we're only given this discrete set of values in a table. Okay, so from that, we're supposed to estimate the temperature of the potato when t equals 46 and when t equals 50. So if we look back at the table, the closest piece of information that we have is this point 45, 296. So we know that at 45 minutes, we were at 296 degrees Fahrenheit. And what we just calculated was an average rate of change, an estimate for how fast the temperature was increasing. So we expect that temperature to go up by 3.85 degrees Fahrenheit per minute. And if we're starting with the temperature from 45 minutes, then it's been 1 additional minute, so times 1 minute. And notice, you don't have to write the units out every time, but I did it here so you could see that what happens is you have the rate in degrees Fahrenheit per minute, and you multiply by the number of minutes, and what you're left with is 296 degrees Fahrenheit plus 3.85 degrees Fahrenheit, and those units make sense, so that's a great sign that we're on track. And if we add that 296 to that 3.85, we get 299.85 degrees Fahrenheit. Okay, we're also asked to do the same thing for t equals 50. So I would still say our closest place to start from is the 296 degrees Fahrenheit at 45 minutes. We could go over to the 60-minute time, but that's further away. So staying closer is better. And now we want to take our 3.85 degrees Fahrenheit per minute. And if we're going from 45 minutes all the way out to 50 minutes, that's 5 minutes out this time. So again, the minutes will cancel, and we're calculating 296 plus 3.85 times 5, which should give us 315.25 degrees Fahrenheit. So basically what we just did with those two calculations is we used our tangent line approximation. So we're not going to dig into that vocab a lot, but I think it's vocab that'll make sense as we keep working on this whole tangent line idea. Basically, if we made a tangent line right at t equals 30 and we followed it out, these are the numbers that it would tell us are the approximate answers for the temperature. That doesn't mean they're spot on. We have our table of data here that shows us what's going on. We don't expect tangent line approximations to be perfect, but the smaller your time interval is, the better those approximations should be. So as long as we don't go too far out, we should be in pretty good shape with these approximations. Okay, the last part of this question is, do we think our answers are over or under estimates? So if you look back at this table, this is just rough, but what I notice is we go up from 70 to about 180, which is roughly 110. And then we go from 180 to about 250, which is roughly 70. And then we go from 250 to 296. In fact, I can include the one in the 6. That looks like 45. And then we go from 296 to about 324, so about 28. And we can probably quit there, but we'll go ahead and look. 24 to 42 is about 18, and 42 to 54 is about 12. So what I notice here, none of those numbers are perfect, but I think I'm in the ballpark, is that the growth is slowing down. So these are all 15-minute time intervals. Again, if the time wasn't equally spaced, we'd have to look really carefully at what's actually happening. But I can see that the jump in temperature is shrinking over time. So if we're starting from 296 and saying it's going up by 3.85 degrees Fahrenheit per minute, over time that 3.85 is actually a little too big. The average rate of change should be shrinking over time. So I think that we probably overestimated everything. We used a bigger average rate of change, and it should be shrinking a little bit over time, especially since our average rate of change was from 15 to 45. So that's going all the way back to 15. If we went from 45 to 75, I think we'd see a decent decrease in our average rate of change. Okay, so hopefully that made sense. Thanks for watching.